Hello everyone, my name is Kiana White and I'll be doing Lab 1 today. First, I will start off by showing the video from Tracker where I observed my observed position and predicted position. Here is the video. As we can see, the orange moves along the x-axis in the positive direction, and the coordinate values are here in this corner. I then graph that here. These are my predicted values, and these are my observed values. According to the video, the x-axis is going in the positive x direction, which you can see here. However, if I had the orange going to the left, you would see a negative graph denoting that the orange went in a negative direction along the x-axis. The y-axis really doesn't play that much of a role, considering that the orange was just along a straight line and we're using no force was acted on it. So here are just the time and the x values. Here is the code after I ran it. As you can see, the position again is in a positive direction, and since there's no net force, we're assuming there's no net force acted on it. We have a straight velocity graph, which means it's at constant direction. If you go here in the code, first, we change ball.pos to the initial. This was the first position on the graph. We then needed to calculate the initial velocity by taking the first 2 points on the graph, graphed by the Tracker app, and the first 2 timestamps, which for me were 0 and 0.03. I then calculated the initial velocity here, which got me this. Putting this in, we can leave these the same, 0, 0.1 for the timestamps. And since we need to change this t, because my last observed timestamp was 0.833. So as long as t, which is time, is greater than, or less than, 0.833, the program will run and calculate over and over again, plotting the values on the graph. We have to change this, stating that the net force is 0. This is F net equals 0. We have to change this formula into the Newton's second law formula, but since F net is 0, that will eventually cancel out if we was doing this on paper and calculating normally, but it's just code. We also have to change the ball's position, which is also positive. These are the formulas that we're ultimately using in the code. We have the V final, which is velocity, equals velocity initial plus F net, which is 0, which is mass. But since F net is 0, mass will ultimately play no role in this equation over change in time, or times change in time. And then for the position update, we have vector final equals vector initial plus the velocity final over change in time. Since we were assuming no net interactions, this made there be no net force, which is proof that this was at constant velocity. Since we set this equal to 0, I'm going to go back down here. Since we set this equal to 0, we know that there is no net force acting on it. So the velocity, there's no change. There's only a positive slope of the ball going forward at a constant speed. There will be no way to tell how many pushes and pulls are acting on this system. The orange is the system, and everything else around it is its surroundings, when we're assuming there's no interaction between the system on, or the surroundings on the system. So therefore, it's just a system. Since we're assuming that there's no surroundings acting on the system, there will be no way to tell how many pushes or pulls are interacting with it, because we don't know what the force is. But if we calculated the net force, we would know the difference between what forces were acting on it, and this velocity graph would probably look a little bit different. And so here are the plotted points. Thank you for listening. Thank you for your time.